In my previous lecture, I was discussing about the chemistry of group 13 elements having S2P1 electronic configuration. While discussing, I discussed about the hydrides of group 13 elements. Among them, you can see aluminum trihydride as well as boron trihydride. Both are unstable. In fact, boron trihydride is not isolated in its monomeric form. Soon after it is made, it undergoes dimerization to have a composition B2H6, that is dimeric, and also I showed you the bonding that happens between two BH3 to stabilize through 3-centered 2-electron bonds. Let us look into some reactions of diborane. In fact, diborane is used to generate higher both anionic and neutral boron hydride clusters. For example, if you take boron hydride such as B2H6, when it is treated with sodium borohydride in diglyme at 363 K, it gives anionic boron hydride Similarly, when you take sodium borohydride having composition B3H8, the same what we have generated here, this reacts with stoichiometric amount of hydrogen chloride to give neutral boron hydride B4H10. Of course, hydrogen gas comes along with sodium chloride. And again this B3H8 anion so either you can write complete formula NaB3H8 or you can also mention as B3H8 minus. This on treatment with stoichiometric amount of HBr gives bromo derivative of boron hydride. And also same reaction at slightly different reaction condition. This is at 373 Kelvin. It gives even higher analog B5H9, a neutral boron hydride. In another interesting reaction, when the sodium borohydride is heated to 435 Kelvin, again in diglyme, it gives dianionic boron hydride Na2B6 H6 plus 5 hydrogen gas will be liberated. So, these are some reactions in which you can see how diborane is used to generate a variety of boron hydride clusters. In fact, the structures of boron hydride would be very interesting. There is one structure bonding concept called Wade's rules that has been proposed to explain bonding in boron hydride compounds. This is essentially originated from valence bond theory concept and valence shell electron pair repulsion theory, and in fact, it is very interesting. However, the details of Wales roots are beyond the scope of this lecture series. As a result, I am not going to go into the details of these, and another fully dedicated course on chemistry of main group elements will be presented by me in 2018 January. That time I will give you more insight into the interesting aspects of Wade's rule and how Wade's rules can be used to explain even other than boron hydride clusters such as zintyl anions and also metal carbonyl clusters and also several p block element clusters, both anionic and neutral, in more details. And you may be wondering what is diglyme. Diglyme is a polyether. So, let me write the structure of diglyme. It is a high boiling ether and its name is 1-methoxy 2-methoxy ethoxy. You can see 2-methoxy ethoxy ethane. This can also be called 2-methoxy ethyl ether, 2-methoxy ethyl ether. This portion, if you just see, it is diethyl ether, and one of the H on CH3 is taken out in both cases, and that H is replaced by OCH3 group, methoxy group, and hence the name 1,2-methoxy ethyl ether, and also this also called di-2-methoxy ethyl ether, and another alternate name for this diglyme is diethylene glycol dimethyl ether. Similarly, if you need even higher temperature, you can conveniently use another polyacyclic ether called triglyme. Okay, let us look into structures of boron hydrides. Just I would show you the structures without elaborating more into the structural details. This is for B4Cl4 tetrahedron, and this is for B9Cl9 tricapped trigonal prism. Of course, how one generated this structure can be seen. This is trigonal prism, and then on each rectangular face you place one boron atom each in this fashion, and then try to connect them to 4 corners of boron atoms in this fashion. Now, each boron atom can have either hydrogen atom or chlorine. So, this is B9H9 or it can be B9Cl9 if it is chlorine. This is called tricapped trigonal prismatic geometry. Similarly, you have B12H12 dianionic compound B12H12 2 minus. So, here you can see this is essentially a icosahedron with each boron having one hydrogen atom. Of course, we also come across many interesting species. For example, if you just look into this octahedral structure here, and just I have shown 2 boron atoms, one is pentagonal bipyramidal geometry I have shown, with one occupying equatorial position, one occupying axial position, and then you can see now it is pentagonal bipyramidal structure, and then from that one by removing 1 or 2 boron atoms, you can generate several other boron cluster types. They can be again either neutral or anionic, and you can see one example that I have shown here. And as I said, from this octahedral geometry you can see here, this is an octahedral, and from this is essentially called closo in one of the structures, and if you remove one of the axial position, it becomes square pyramid. This is called nido, and if you remove one more boron atom from equatorial position, this is called arachno. This is how you can derive from starting from fundamental structural geometry closo to either nido by removing one boron atom or removing 2 boron atoms to arachno, and one such example I have shown here B6H6 2 minus. This has octahedral geometry, and now after removing this one, we have 5 boron atoms. This has nido square pyramidal geometry, and if you remove one more, it becomes B4H10. Have arachno structure like that. There are some rules are there. Using those rules, one can conveniently explain all the structures starting from simple geometries. Let us look into the preparation of diboron. Since diboron is very important, industrial production of diboron involves the reaction of BF3 with sodium hydride. For example, here BF3 when it is treated with sodium hydride, it gives diboron and 6 NaF. Okay. And B2H6 is a colorless highly toxic gas, catches fire spontaneously upon exposure to air. One has to be very careful while handling this one, burns in oxygen releasing an enormous amount of energy. For example, when B2H6 is subjected to oxidation or interaction with oxygen, it forms boron trioxide and 3 molecules of water will be formed along with enormous energy. You can see here delta Hc value is minus 1976 kilojoules per mole. So, this explains the exothermic nature of this reaction. Okay. And of course, on exposure to moisture, B2H6 undergoes hydrolysis to form boric acid. Okay. And B2H6 when it is treated with Lewis bases such as trimethylamine, it readily breaks into monomeric units and forms an adduct with trimethylamine. Similarly, when you treat this one with 2 equivalents of carbon monoxide, it gives, it forms an adduct. Since boron hydride or B2H6 is Lewis acidic in nature, and in order to overcome its Lewis acidic nature and also overcome the electron deficiency, BH3 undergoes dimerization to form B2H6. In absence of any Lewis base, it remains intact, of course, in absence of moisture or air. On the other hand, when it is exposed to strong Lewis bases such as trimethylamine, it breaks into monomeric forms and forms an adduct in this fashion. Now, this is an acid base complex, or you can also call it as an adduct, and same thing is true in case of the interaction of diboron with carbon monoxide. B2H6 when it is reacted with ammonia, it gives an adduct to start with. So, when diboron is treated with ammonia, initially it forms an adduct of this type. You can see here BH2NH3 twice cation and BH4 anion is there. This on further heating, it gives a compound having composition B3 N3 H6 called borosine or inorganic benzene. You can see the structure of this one, and here the BH bonds distance is about 120 picometer or 1.2 angstrom units, and BN bond distance is 1.44 angstrom units or 144 picometer, and NH bond distance is 102 picometer, and this one is called inorganic benzene. So, let us look into some uses of group 13 elements. As I said, when we talk about the group 13 elements, another important compound is sodium borohydride. I did not give the preparation of sodium borohydride. So, this can be prepared starting from trimethoxyborane, interacting this one with sodium hydride will give you sodium borohydride through the formation of sodium methoxide. Okay. And this is a very good reducing agent. I would discuss more of its properties in another 2 to 3 minutes. Just I will show you one example how it is used in transmetal chemistry to reduce some of the transmetal derivatives. For example, if you take titanosin dichloride, that is called Cp2TiCl2, this one when it is treated with 4 equivalents of sodium borohydride, that means reaction of titanosin dichloride and sodium borohydride in 1:2 ratio, this gives Cp2TiBH4 plus 4 NaCl plus B2H6 comes out along with 1 equivalent of hydrogen. In the presence of metal catalysts, sodium borohydride releases hydrogen. Exploiting this reactivity, sodium borohydride is used in prototypes of the direct borohydride fuel cell. Of course, we have hydrogen fuel cell, methanol fuel cell, many such interesting devices to generate hydrogen as an alternate source of energy. The hydrogen is generated for a fuel cell by catalytic decomposition of aqueous solution of sodium borohydride. In the following reaction, I will show you that. So, when you subject sodium borohydride to hydrolysis, NaBO2 is formed with the liberation of 4 equivalents of hydrogen. Here delta H is less than 0. So, as a result, this is used in generation of hydrogen in borohydride fuel cell. Boron is extremely hard, refractory, low density solid of high melting point and very low electrical conductivity. As a result, boron fibers are used in making bulletproof vests and light composite material for aircraft purposes. And as I had mentioned, boron has 2 isotopes, one 10 boron is about 19% abundant and 11 boron, that is 81% abundant. 10 boron isotope has very high ability to capture neutrons. As a result, metal borides containing 10 boron are used in nuclear applications as protective shields and also as control rods, and borax and boric acid in making heat resistant glasses, of course Pyrex glass and also borosilicate glasses, glass wool and also in fiberglass applications, and borax as a flux in soldering metals, medicinal soaps. Orthoboric acid is also used as a mild antiseptic agent. Okay. And aluminum is a bright silvery white metal with very high tensile strength, and it has high electrical and thermal conductivity, and in fact electrical conductivity of aluminum is twice that of copper if you consider weight to weight basis. To make alloys of copper, manganese, magnesium, silicon and tin, aluminum is used. Aluminum can be drawn into thin wires or plates or foils and sheets, and hence they are used in packing. Especially you have seen food, processed food and fast food and ready to eat food all packed in aluminum, and also aluminum is widely used in utensil making and also construction and also in aircraft engineering. As I mentioned, sodium borohydride and lithium aluminum hydride are very important compounds in inorganic and as well as organic synthesis. They are extensively used in organic chemistry. And how to prepare this lithium aluminum hydride? I will show you the preparation. There are several methods are there to prepare lithium aluminum hydride. One such method involves the treatment of lithium hydride with aluminum trichloride that results in the formation of lithium aluminum hydride plus 3 lithium chloride comes out. And of course, this reaction has to be carried out in ether solution, preferably in diethyl ether, and addition of further quantities of aluminum trichloride in ether solution yields an ethereal solution of AlH3. That means, you can isolate aluminum trihydride as an adduct of ether. So, if you take lithium aluminum hydride in a ether solution and treat with aluminum trichloride again, that generates AlH3. As you know, this is unstable, and I have shown here essentially in ether solution it forms something like this. It forms an adduct plus LiCl is formed, and also at very high temperature, by combining lithium metal and aluminum metal with high pressure of oxygen, one can also generate lithium aluminum hydride, Li plus Al plus 2H2. Under high temperature and high pressure, one can generate AlH4, lithium aluminum hydride. Okay. Of course, the utility of lithium aluminum hydride as a reducing agent in inorganic and organic synthesis is extensive. I will show you few examples here. When you treat silicon tetrachloride with lithium aluminum hydride, you can get silane, SiH4. Silicon tetrahydride is also called silane, very similar to we call methane for CH4. Similarly, when you take lithium aluminum hydride and interact with dimethyl tin chloride, the corresponding dimethyl stannane can be generated. Dimethyl tin dihydride. If you take dimethyl zinc instead of these, you can also generate zinc dihydride, but these are all highly reactive and highly pyrophoric compounds. One has to handle extremely in the absence of air or moisture under strictly inert atmospheric conditions. Methyl, I am writing CH3 methyl. If you take lithium aluminum hydride and interact with dimethyl zinc, here what we get is AlMe2 H2 plus zinc hydride. So, these are some of the applications in synthesis. Of course, we have plenty of applications of lithium aluminum hydride in organic synthesis. I will show you a couple of examples here. More you can find in any organic chemistry textbook. For example, if you take an aldehyde and treat this one with lithium aluminum hydride, it gives the corresponding primary alcohol, and if you take a ketone, it gives secondary alcohol. If you take an acid, it again gives primary alcohol. And if you take acid chloride, it gives again primary alcohol. So, like this one can keep on performing these reactions. You can take an amide and gives amine. Primary amine. So, one can use as a very good reducing agent to generate a lot of organic products. Let us look into some of the questions that comes to your mind. So, I have put a title to this slide, ask a question yourself. I have put some questions here. The first question is, BCl3 is a volatile liquid, so highly volatile. Suggest a way in which it can be more conveniently handled. If it is highly volatile, weighing out a known amount of stoichiometric amount for a particular reaction is very difficult, and especially in a open system where moisture is very high, humidity is very high, it is next to impossible. Of course, we have to use special conditions like glove box and inert atmospheric techniques, high vacuum techniques, all those things. However, still it is not easy. In such conditions, if you want to use this volatile liquid, is there any alternate? Yes. For example, if you take boron trichloride and if you interact with a Lewis base such as SME2, it forms a adduct and it is solid. So, volatile liquid, after making an adduct with dimethyl sulfide, it becomes solid. Now, it is little less reactive, so that one can handle conveniently. So, boron trichloride is essentially sold in the form of a SME2 adduct. And of course, one should be extremely careful while making the adducts. You should not use a very strong base such as trimethylamine. In that case, what happens? It forms a very strong adduct. In such case, when you want to use it, it may not be easy to release BCl3 for further utility. So, always use a mild interacting base and make the adduct. And of course, these adducts can also be released when you use other Lewis bases such as phosphines and various other amines. So, I have given you here, you can see the answer. So, adducts of BCl3 will be less volatile than BCl3 itself. So, adduct of dimethyl sulfide, that is Me2S BCl3, is a crystalline solid which is very easy to handle and it is less sensitive towards hydrolysis than BCl3. Let us look into another question. So, although fluorine is more electronegative than chlorine, why BCl3 is stronger Lewis acid than BF3? For this one, I had already discussed it in my previous lecture. If you just look into BF3 structure and BCl3 structure, and in case of BF3, we have one empty p orbital that is perpendicular to the plane of BF3 molecule. Okay. So, this one can interact with filled p orbitals of F. As a result, there can be some multiple bonding interaction, and this removes to an extent electron deficiency of boron, making it less Lewis acidic in nature. In contrast, if you look into boron trichloride, we have to utilize 3p orbitals. Since there is a difference in the size of 2p and 3p, this overlapping is not effective. As a result, there is not effective transferring of p electrons from chlorine to boron. As a result, what happens? Boron remains as electron deficient and strong Lewis acid, and hence it is stronger Lewis acid compared to BF3. Let us look into another few questions. Look into these questions here. I have given some incomplete chemical reactions. For example, if you treat BF3 adduct of NMe3 with BCl3, what would happen? You know, just now I discussed and informed you that BF3 is a weak Lewis acid compared to BCl3, and BCl3 is a stronger one in the first equation. So, BCl3 replaces BF3. So, what you get is here BCl3 replaces BF3 from the adduct to form BCl3 NMe3 adduct, and BF3 comes out. And in the next reaction, since BCl3 is already formed an adduct with trimethylamine, I do not think BF3 can replace it. So, in the second equation there is no reaction takes place. And the third one, BH3 adduct of SME2 is there, that is when treated with trimethylamine being a stronger base, it readily replaces SME to form BH3 NMe3 adduct. In contrast, in the fourth equation, we have a BH3 NMe3 that is allowed to interact with SME2. Obviously, there will not be any reaction. So, no reaction. Okay. So, a borane contains, so another question is there, a borane contains 84.2% boron and 15.7% hydrogen by elemental analysis, and has a molecular mass of 76.7. So, that means we have a boron hydride, its molecular weight is 76.7, that contains 84.2 percentage of boron and 15.7 percentage of hydrogen. You have to determine its molecular formula. Of course, here what you need is the atomic weights of boron and hydrogen. It is given here. For boron 10.811 and for hydrogen it is 1.0079. One can make an attempt to calculate that one. It is very simple. You can do it using two methods. First, look into boron. So, here 84.4% is there, and divided by 10.88811, you get 7.788. Similarly, H, you can perform the same calculation. 15.71 is the percentage, and its atomic weight is, this gives 15.58, and if you look into H2B ratio, it is 15.58 to 7.788. So, it is 1:2 ratio, what you get is 1:2. So, or you can also do by other means. So, 84.2%. So, what is its in the molecular weight of 76.7. So, this gives 5.97, you can consider approximately as 6. This is for boron, and similarly for hydrogen, this is 15.71 divided by 100, that is the percentage, into that is given is 76.7 is the molecular weight of the compound. So, here you get at the end 11.595, approximately you can take it as 12. So, that means here if you simply you can write the molecular formula as B6H12. Now, if you calculate the molecular weight, it comes around 76.7. So, this is how you can calculate the molecular weight and arrive at the right molecular formula of the boron hydride. Borosine reacts with 3 equivalents of hydrochloric acid to give a material of composition B3N3H9Cl3. just look into that equation. So, what is asked is write the structure of the compound, and then the next question is how does benzene, which is isoelectronic with borosine, reacts with hydrochloric acid. So, Bn bonds are polarized due to the difference in the electronegativity of boron and nitrogen. So, boron carries partial positive charge and nitrogen carries partial negative charge. So, one can write the structure something like this. This is the structure of borosine, and borosine we have partial positive charge on boron and partial negative charge on nitrogen. So, now we have HCl. HCl is polarized. When it is polarized, H will be carrying positive charge and Cl will be carrying negative charge. So, obviously, you can expect the chlorine to go to boron and hydrogen to go to nitrogen. As a result, you get this product. This is the outcome of interaction of borosine with 3 equivalents of hydrochloric acid. So, this ends the chemistry of group 13 elements. So, before I conclude the chemistry of group 13 elements, let me summarize the salient features. Except for boron, other elements starting from aluminum to thallium have low electronegativity value and all are metals. Only boron is non-metal in this group and rest of the elements are metals. The +3 oxygen state dominates the chemistry of group 13 elements, and inert pair effect appears for the first time among p block elements. For example, the the +1 oxygen state for thallium is moderately stable, and of course, +3 compounds of thallium are oxidizing in nature, and boron forms a large number of neutral and ionic boron hydride clusters as a result of its electron deficiency, and all boron trihalides are Lewis acids. In fact, Lewis acidity for boron trichloride is more than boron trifluoride. Of course, in case of boron trifluoride, there is a scope for p-pi overlapping, through which some of the fluorine electrons are delocalized into the empty p orbitals of boron. As a result, BF3 is comparatively less Lewis acidic in nature compared to BCl3, and sodium borohydride and lithium borohydride. Sodium borohydride and lithium aluminum hydride find applications as very useful reducing agents in inorganic and organic synthesis. Let us move on to the chemistry of group 14 elements. I have shown here group 14 elements having Ns2 Np2 electronic configuration, and starts with carbon, silicon, and then we have germanium, tin and lead lie in the center of main group elements, because 13, 14, 15, 16, 17, it is exactly at the middle of the main group elements, considering 2 s block and 1 p block. Carbon, again the 7th most abundant element in the Earth's crust. In nature, it occurs both in free and in combined state. Of course, when we talk about free state, coal, diamond and graphite, and in the form of combined state we have metal carbonates in the Earth's crust, and also hydrocarbons, fossil fuels, and also carbon dioxide constitutes about 0.03% in air. Carbon is the most versatile among all elements in the periodic table. And what are the special features of group 14 elements? Just you can see the periodic changes among the chemistry of these elements is very interesting, that we can elaborate later when we look into the reactivity of group 14 elements. And the stability and abundance of CC bonded compounds is again very interesting and fascinating. The importance of pi bonding in carbon compounds is again important, that leads to an array of compounds having polymeric structure and cyclic structure and several other interesting features. They show major differences from the lightest element carbon, again no exception, similar to any other S and P block element. First element is unique because of its smaller size, and it differs significantly compared to the rest of the elements, and here carbon is no exception, being a lightest element. It is little different, and however, it is a typical non-metal, and when you go towards the higher analogues of the group, they are main group metals. Okay. For example, lead is a main group metal, and tin is there. So, the group oxygen state is +4, and very important for carbon and silicon, and it may not be to an extent it is important for germanium, it may not be that important in case of tin and lead. And in hydrocarbons, the oxidation is formally -4, because hydrogen is less electronegative compared to carbon. Carbon carries -4, for example, methane if you take. These compounds are thermodynamically unstable, but an extremely important class of compounds which have constituted the rich branch of organic chemistry. And what are the other features of group 14 elements? Germanium is there, the third one in the series, shows some stable +2 compounds such as germanium iodide, although +4 state is predominant, and tin shows both +2 and +4 state, and +2 is reducing in nature and +4 is oxidizing in nature, and whereas lead 4+ is oxidizing and lead 2+ compounds are stable. For example, if you make PbO2 is a very powerful oxidizing agent. And these elements, the carbon, silicon, germanium, tin and lead, in principle should show stable +2 oxygen state just utilizing 2 p electrons. Promotion of an electron from s orbital, that is filled ns2 to np, requires little higher energy, but the atoms can now form 4 bonds. That is the only advantage by promoting 1 electron. So, that now we will be having ns1 and p3 electronic configuration. So, it makes 4 orbitals having 1 electron each can readily form covalent bonds or polar covalent bonds. But however, more energy produced by bond formation for carbon and silicon offsets the cost of promoting an s electron. That means, essentially when you have to promote prior to any reaction one of the s electron to the p, it requires some energy, and now to what extent the energy required to promote an s electron is compensated by the covalent bond formation with other atoms is what matters. In case the energy released during the formation of the bond is more than compensating the energy required to promote s electron to the p, then basically what happens, s electron can be readily promoted and one can have a tetravalency, that means +4 oxygen state can be seen, and this is what exactly happens in case of carbon and silicon. And of course, when you look into the bond strength obviously decreases down the group. An important feature of group 14 elements is catenation, which is less important down the group. Catenation is extensive in case of carbon, to an extent one can see in case of silicon. As we move to germanium, not much is there, but we have examples of having germanium 4 to 5 up to 6, 9 in one chain, whereas in case of tin and lead it is less extensive. And important source of carbon are coal and crude oil and natural gas. In natural gas, it is mainly in the form of methane, and carbon shows allotropy, graphite, diamond, they are crystalline forms, soot is amorphous form, and catenation is nothing but the formation of rings and chains by atoms of the same element. After carbon, perhaps sulfur forms the next largest number of catenated compounds, both linear but more of cyclic, that I would be elaborating when I discuss chemistry of group 16 elements. And this is the structure of graphite. You can see in the graphite each carbon has undergone sp2 hybridization and is essentially it is fusing benzene rings together. You can see here. And I have also shown here, if you just see this one, this is the separation between graphite layers, and this separation is 335 picometer, and the carbon-carbon distance in graphite is 1.42 angstrom units or 142 picometer. This is the structure of diamond, and as I said, graphite you can visualize here, it appears like fused benzene rings. these layers are there. Another layer comes at a distance of about 334 picometer. In case of diamond, what happens? We have a tetrahedron like this. This is a carbon having 4 bonds, and again each one is having a another carbon, and it continues like this. One can start like this. You can keep on adding just carbons, no other atom, no other element. So, when you are doing it like this, basically what happens is you can see this cyclohexyl type rings, and this continues in all the directions, giving a 3-dimensional structure in case of diamond. This is how you can explain the bonding in diamond. So, something like this. So, this will continue. You can clearly see here, essentially start connecting the tetrahedral ends with tetrahedral ends of carbon, and you will have this kind of structure, and a monomeric unit I have shown here, and this is another figure that shows the structure of diamond. And of course, besides these three, various other allotropes of carbon are there. You can see here A represents diamond, and B represent graphite layers, and then C is lansodylite, and it is nothing but hexagonal allotrope of carbon allotrope diamond, believed to form when meteoric graphite falls to earth. And then this is D is C60 fullerene, and then this is C70 fullerene, and this is amorphous carbon, and also this is single walled carbon nanotube. So, like that, and of course, these are all essentially originated from graphite, monolayer graphite, and their different type of arrangement led to the formation of some of those other allotropic forms. In graphite, the carbon atom form planar sheets of 6-membered rings, this one. The remaining pz orbitals form extensive delocalized pi system over the sheet. That is the reason they are kept at a distance. Attraction between adjacent sheets is very weak. So, the graphite slide over each other very easily. Graphite structure is unique for carbon among group 14 elements, because the small pz orbitals on carbon can overlap effectively to form the delocalized pi system. So, when another one comes, because this pi delocalized interaction, okay, so they have some sort of pi-pi interaction. In contrast, diamond has 3-dimensional network structure made up of tetrahedral carbon atoms forming strong covalent bonds with each other. Diamond is one of the hardest substances known. In fact, its melting point is more than 3550 degrees centigrade, and it is made up of just carbon atoms. And another molecular allotrope of carbon is called fullerene, I showed you. First one to be discovered is C60, consists of 5 and 6 membered rings, also called as buckyballs after the architect or Buckminster Fuller, who designed geodesic domes. Next, now let me pose a question. The melting point of diamond and graphite are greater than 3550 degrees centigrade, but C60 fullerene sublimes between 450 to 500 degrees centigrade. So, how to explain this one? We know by definition what is melting point. So, when you are melting, essentially we have to overcome the lattice energy that holds molecules or atoms together. In case of C60, what happens in the solid state, C60 molecules are held together in the lattice energy. And when you start heating, essentially the whatever the interaction that are there between 60 units, molecular units, they are essentially loosened, and as a result each C60 comes out. So, that is we call it as melting point of fullerene, whereas in case of diamond and graphite, in order to melt we have to break 4 bonds or 3 bonds in case of graphite and 4 bonds in case of diamond. That means essentially have to break all CC bonds. That is the reason it requires enormous energy. That is the reason there is enormous differences there in the melting points of graphite and diamond with respect to fullerene. And we have other 4 elements like silicon, germanium, tin and lead. Silicon is the most abundant element after oxygen in the earth's crust and occurs as mainly silica and silicate minerals. Germanium is least common and occurs in some zinc and silver ores in trace amounts and also in flue dust and the ashes of certain types of coal. Silicon and germanium adopt diamond like structure, they do not show allotropes, but if you look into free silicon and germanium, their structures are very similar to diamond structures. And tin mainly occurs as cassiterite, that is SnO2 is called cassiterite, from which metallic tin is obtained by reduction. The main ore of lead is galena, that is a sulphide ore, that is called PBS, which is roasted in air to form lead oxide, which is then reduced to the metal using CO in blast furnace. Of course, in metallurgy we use either carbon monoxide, carbon in reduction. That information comes from Illingham diagram. So, here in case of lead sulphide also, first it is converted into lead oxide and then it is reduced using carbon monoxide in blast furnace. Lead is a typical heavy metal. I will stop at this stage and we shall look into the chemistry of group 14 elements in the next lecture. Until then, thank you very much.